Welcome back, folks, to Precalculus. Today we're in Chapter 3, Section 3, talking about polynomial and rational functions. Okay, so just to review, a polynomial of degree n, a complex one, is in the form of a sub n times x to the n, and then it goes in descending order by power, all the way down till you get to some constant, okay, where those a's are all your coefficients. And just to review the fundamental theorem of algebra, it states that every function with a degree of at least 1 has at least one complex 0. Now, the linear factorization theorem sounds a little bit more difficult than it actually is. It basically says that a polynomial with degree greater than or equal to 1, then it has exactly that many factors. Okay? So the factors are going to match the degree. It's important to note that if one of these factors of p occurs more than one time, so m times, then it is said to have a multiplicity of m. Okay, so an example of a factor happening more than once would be, let's say we have the factor x minus 3 to the 5th power. There it is happening 5 times. There's a multiplicity of 5. And that's going to have unique characteristics as well. So we know that complex factors always occur in conjugate pairs. And lastly, if a polynomial has a degree of n, then we know it has exactly n zeros. Okay, and we'll be finding all of those in this section as well. Okay, so let's dive straight into an example here and find some zeros and multiplicities, talk about what's happening there. So here we have this polynomial that's kind of factored for us, and we're being asked to factor the rest of it. Okay, so first of all, to factor this first one, it's an AC method. 2 times negative 3, I'll write it over here as negative 6. Factors of negative 6 that add up to be negative 1 are negative 3 and 2. So we can go ahead and rewrite this as 2x squared minus 3x plus 2x minus 3. We're going to go ahead and group. And we're going to pull out an x. Leaves us with a 2x minus 3. And we're going to pull out a 1, which leaves us with a 2x minus 3. So just that little piece factors into 2x minus 3, x plus 1. Now let's take a look at this next part of the polynomial right here, x squared minus 3x minus 4. Okay, factors of negative 4 that add up to be negative 3 are x minus 4, x plus 1. And then we still have that x minus 4 on the end. So simplifying this one more step, nothing can happen to the 2x minus 3. But we see we have 2 of these x plus 1s. So I'm going to write x plus 1 squared. And we have 2 of these x minus 4s. So I'm going to write x minus 4 squared. So using the zero product property, we can see that our zeros are 3 halves, negative 1, and 4. You're probably asking, well, this was supposed to be a 5th degree polynomial. How do I only have 3 zeros? Well, you have 3 zeros because this one right here has a multiplicity of 2, and this one right here has a multiplicity of 2. Which, if you remember back to Algebra 2, we'll talk more in the future, that means that your graph is going to bounce off the x-axis at these 2 values. It is going to cross the x-axis at this value. So just fun facts, but notice the multiplicity there. We'll talk about more later. Okay, so now, if we're looking here, we want to find the equation of degree 4 that has zeros 3, 3i, and negative 2. Well, you're probably saying, well, how could it be degree 4 if you only gave us 3 zeros? But if we remember, complex factors must occur in conjugate pairs. So if 3i is a 0, then we automatically know negative 3i is also a 0. So let's go through and use our zeros to make the polynomial. So if 3 is a 0, that means x minus 3 is a factor. I'm going to go ahead and jump to negative 2. If negative 2 is a 0, then x plus 2 is a factor. Now, if 3i and negative 3i are zeros, that means that we took the square root of negative 9, which means that the zero product property leads us to x squared plus 9 being a factor. Okay, let's move on and let's talk a little bit about the intermediate value theorem. So the intermediate value theorem is a glorified way of saying something very simple. Okay, it's saying that if you have a polynomial, that means it's continuous, that if you have a point, if you have an a value that you plug in and a b value that you plug in, and they get opposite signs, then there must be a value in between there such that it crosses the x-axis and you get a 0. So if you think about it, like let's just say this is a and this is b. And when you plug in a into our polynomial, you get that value. Let's say it's negative. And then you plug in a value over here into your polynomial, and you get a positive number. That means that somewhere along the line, there must be a c value such that p of c is equal to 0. That's all the intermediate value theorem is saying. So let's go ahead and just practice it right now. So if we have this polynomial right here, g of x, okay, and we think that it has at least one 0 between negative 3 and 1. Well, let's plug in negative 3 and see what we get. Negative 3 times 3 cubed minus 5 times negative 3 minus 12. So that would be negative 27, positive 81, plus 15, minus 12, equals 84. Okay, that's a positive number. So now if we plug in 1, let's see what we get. So we got negative 3 minus 5 minus 12 is negative 20. So the fact that one of these is positive and one of these is negative means that somewhere in between negative 3 and 1, there's a 0. At least one 0. Okay, and that's all the intermediate value theorem is saying. Okay, so now let's talk a little bit about the rational root theorem, or the rational zeros theorem. So what the rational zeros theorem is saying is, like, if you want to find out if there's any rational zeros for a function or a polynomial, if they exist, they are going to be of the form p over q, where p is a factor of the constant term, or the number at the end, and q is a factor of the leading coefficient. This will make more sense when we start to use it in practice. So let's just make a really quick example, and let's just say our function is equal to 2x squared plus 7x minus, let's say, 6. So if we have rational zeros, the rational root theorem says if they exist, they're going to look like factors of the constant divided by factors of the leading coefficient. So those are going to be plus or minus 1, plus or minus 2, plus or minus 3, and plus or minus 6, divided by plus or minus 1, plus or minus 2. So every combination of that. So 1 over 1, 1 over 2, 2 over 1, 2 over 2, 3 over 1, 3 over 2, 6 over 1, 6 over 2, and all the negative versions and variations of that are going to be possible zeros. We don't know if they're zeros, but if they do have rational zeros, it's going to look like this. Okay, the rational root theorem also has this neat little corollary that says if the sum of all the coefficients is 0, if you add up all the coefficients and you get 0, that means you already know 1 is a root, 1 is a 0, which means x minus 1 is a factor. It also says that if you change the sign of all the terms with an odd degree and the sum is still 0 of those coefficients, then -1 is a root, or 0. And x plus 1 is a factor. So let's just make up one that has a 1 as a 0. So if we said x squared plus 2x minus 3. 1 plus 2 is 3, minus 3 is 0. So 1 should be a 0. Now let's go ahead and just see if it does factor like that. If we factor this, we get x plus 3, x minus 1, and you can see that x minus 1 is a factor, meaning 1 is a 0. So let's try it with the with this to see if we can make an example where -1 is a 0. Okay, so let's just say we start with the function x squared minus 2x minus 3. Okay, now we have to change, so I like to use a different color to do that. We have to change the odd degree ones, so that would change this to a plus right there, because this odd degree x to the first power, let's change the sign on it, and then let's add up those coefficients. 1 plus 2 is 3, minus 3 is 0. So it should work that -1 is a 0 and x plus 1 is a factor. Let's go ahead and factor the original equation. It should factor into x minus 3, x plus 1. There you go. Pretty cool. Okay, for this next example, I'd like you guys to pause your video and see if you can find the possible rational zeros of this polynomial. Okay, noting that 42 is the constant and 3 is the leading coefficient. Very, very similar to what we did right here. Okay, under the rational root theorem. Okay, so pause your video, take a quick moment, and see if you can find all the possible rational zeros for this polynomial. Okay, so let's take a look now at this next example, trying to find all possible zeros of this function. Now, a good rule of thumb would be to always check and see if your coefficients add up to be 1, and then if that doesn't work, check your odd degree coefficients, and see if now those add up to be 0. I'm sorry, add up all your coefficients to see if there's 0, see if 1 is a 0, or change your odd degree ones and then add them up to see if -1 is a 0. Okay, so let's just go ahead and check it out. So if we add this coefficient 1 plus -3 is -2, plus 4 is 2, minus 2 is 0. So that means that 1 is a 0. And let's go ahead and prove it. So do a little synthetic division. Let's see what we get. Bring the first term down, multiply. Multiply. Add, and boom. There we go. We know that 1 is a 0. So if we try to write this, we can write it as x minus 1. And then our leftover factor is x squared minus 2x plus 2. Okay, so if you're looking at it, you're thinking, what factors, let's try to find the other zeros here. What factors of 2 add up to be -2? Well, there are none. So we have to use the quadratic formula. So minus the square root of b squared minus 4ac all over 2a. We should get, let's see what we get. 4 minus 8, -4 over 2, 2 plus or minus 2i over 2. Everything divides by 2, so 1 plus or minus I. So our zeros are 1 plus or minus I and 1, which we found earlier. Pretty cool. Okay, so let's talk lastly about Descartes' rule of signs and then how it relates to upper and lower bounds later. But So the number of positive real zeros, meaning the number of times your polynomial is going to hit the x-axis on the right side of the y-axis, or the positive x-axis, is equal to the number of variations in sign, or an even number less. And we'll talk more about that as you start to get it. The number of negative real zeros, meaning left side of the x-axis, x-intercepts, is equal to the number of variations in sign for p of negative x, or an even number less. So essentially, we're just going to be changing the odd degree terms again and counting how many variations we see there. So if we look at a polynomial here, and I'm just going to make one up on the spot. Let's say we got x to the fifth minus 2x cubed plus x squared plus x minus 1. Okay, so let's go ahead and count the number of variations in sign. So it starts positive, it goes to negative, that's 1. Then it changes back to positive, that's 2. Stays there, no change. Goes back to negative 3. So that means there is 3 or an even number less, so 1 positive zeros. Okay, now let's go through and let's change the odd degree ones, just the odd degree ones. So that'll be negative x to the fifth plus 2x cubed plus x squared minus x minus 1. And now it's time to count up the number of variations. So start at negative, goes to positive, that's 1, stays positive, goes to negative, that's 2, stays negative. So there's either 2 or an even number less, so 0, negative zeros. So there's either 2 x-intercepts on the left side of the x-axis, or there's no x-intercepts on the left side of the x-axis. There's not going to be 1 or 3 or 4 or 5 or anything like that. Okay, let's talk a little bit about upper and lower bounds. So what this is saying is basically, I'll just make it like really easy to understand, is if you do synthetic division and in your quotient row you get all positive or 0, then whatever number you did with synthetic division is an upper bound, meaning there are no zeros bigger than whatever you did synthetic division with. If you do synthetic division and everything in the quotient row alternates signs, then you know that that value is a lower bound, meaning there's no x-intercepts less than that. Okay, so you can kind of use this upper and lower bound to kind of hone in and say there's nothing bigger than this, there's nothing smaller than this, so all of my zeros, you know how to count zeros, have to be between there and there. So we have all these tools that tell us where to find zeros. So let's just go ahead and do a really brief, quick example here. Let's just say I've got p of x is equal to x squared plus 3x plus 5. And I'm going to say I think the upper bound is 7. Okay, I don't think there's going to be zeros bigger than 7. So let's just do 7, 10, 70, 75. Everything is positive or 0, so positive. So no, there's no zeros for this polynomial that are bigger than 7. Okay, now let's do the same polynomial. 1, 3, 5. I'm going to say negative 6. I don't know that for sure, but we'll find out. 1, negative 6, that'd be negative 3, 18, 23. So because they alternate positive, negative, positive, that means there's no x-intercepts that are less than negative 6. Pretty cool there too. So bring your questions to class. I look forward to helping you and doing some examples together.